So, in this lecture we will try to solve some problems related to convolutional code and in general. So, the first question that we will try to answer is, if you want to do reliable communication in presence of an additive wide Gaussian noise channel, and of course, we have infinite bandwidth, what is the minimum signal to noise ratio required? So, for that we first need the expression for capacity of additive wide Gaussian noise channel, and the capacity of additive wide Gaussian noise channel is given by this expression, where W is the bandwidth, S is my signaling power, N naught by 2 is two sided power spectral density. Now, so we are considering when bandwidth is infinite. So, this can be written. So, this will be log 1 plus when W is infinite, then this will go to 0. So, log of 1 will be 0 and 1 by W will also go to 0. So, it is 0 by 0 form. So, we will differentiate and we can find out that the capacity when bandwidth is infinite is given by this expression, S by N naught natural log of 2 bits per second. So, we are interested in transmitting k bits over tau seconds. So, if we do that, where tau is some multiple of time period t. So, if we do that, our energy per bit is given by S tau by k. This S was my signaling power, we are sending over time t, tau, and total number of information bits was k. So, energy per bit is S tau divided by k. Now, our transmission, because we are transmitting k bits over time tau, so our transmission rate is k by tau bits per second, and our energy per bit that we wrote here is basically S tau by k, and k by tau is RT. So, we can write energy per bit in terms of signaling power and transmission rate R of t. So, if we divide our expression for channel capacity by RT, what we get is this expression. Now, we know from Shannon noisy channel coding theorem that as long as transmission rate is less than channel capacity, we can reliably communicate over the communication channel. So, we want RT to be less than this channel capacity. So, if we want this to hold, then we get a condition on signal to noise ratio. So, we get this following condition on energy per bit. So, SNR per information bit, we get this condition that SNR per information bit should be greater than 1 minus 1.6 dB. This is for the case when we have infinite bandwidth and our code rate can actually go to 0. So, signal to noise ratio then cannot be less than this limit, which is minus 1.6 dB. Okay, let us look at next problem. So, we are interested in reliable communication over additive wide Gaussian noise channel, and we are transmitting using a rate k by n code. So, what is the effect of the bandwidth W? Now, we know if for a band limited channel, the capacity is given by this expression, Okay. So, let us say we are transmitting at Nyquist rate. So, we are transmitting at 2W samples per second and we are using a rate k by n code. So, if we transmit k information bits during time tau, then number of samples per code word that we are sending is 2W tau. Now, our transmission rate is k information bits over tau time. So, our transmission rate is k by tau and this we can write in terms of these samples per code word n, which is given by this expression, and k by n is nothing but our code rate. So, this transmission rate is given by 2WR, where R is my code rate. So, this many bits per second is my transmission rate. Now, we know that energy per bit is given by signaling power by transmission rate. This we have done in the last example. We had this, right. So, using this, then, so if we do that, we can write S by W n naught in terms of EB by n naught. This is equal to 2 times code rate by into SNR per information bit. So, in this expression of capacity of band limited channel, we can replace this expression by this. Fine. Now, for reliable communication, we know that our transmission rate should be less than channel capacity. And what is channel capacity? That is for the band limited channel, it is W log of 1 plus S by W n naught, which is basically given by this expression. So, a transmission rate which is 2 times WR should be less than W log of 1 plus 2R EB by n naught. So, from here then we can write down the expression for minimum SNR, information bit, energy per information bit by noise power structure density. So, SNR per information bit, we can write it as this is should be greater than equal to 2 raised to power 2R minus 1 divided by 2R. Now, this right hand side term is an increasing function of R. So, if you want to communicate close to the channel limit, then your information rate RT as well as code rate R should be close to 0. In fact, if you let R go to 0, what you will see is you will get the limit that we had just talked about in the previous problem, which was minus 1.6 dB. And if let us plug in some practical values of R, let us say R is half. If we put value of R to be half, then EB by naught should be more than 0 dB. So, you can see for any rate which is away from 0, then this minimum SNR required for transmission is also more. Okay. Now, the next question that we will solve is to prove that for every convolutional code has a generator matrix which is delay free. Now, delay free meaning, so basically if we have a generator matrix, let us say of the form di and then something like 1 plus d and some dj 1 plus d square or something like that, we can always write an equivalent generator matrix which will be free of these like delay terms. I will talk about that. So, let us see if we have a generator matrix G of d. okay, and its non-zero entries can be written in this particular form. So there is some delay term, we calling it ds t raised to power sij, and then we have this rational function, which is fijd by qijd, and fijd and qijd is of the form 1 plus some f naught d plus and this is 1 plus q naught d plus something something. Okay. So that is what I meant, f0 and qij0 is 1. So any entry in the generator matrix can be written in this form. Okay. Now, what is this term Sij? It is essentially a delay term. So if we have some term like Sij, so what you will get is terms of this particular form. Now, if we consider S, which is the minimum Sij over all I and j, then we can find an equivalent generator matrix which would be g dash of d, which we can write as d minus s gd, and this gid will be delay free and it is of course realizable, and it also generate the same set of code words. So whenever we have a generator matrix which has a delay term, we can always find an equivalent generator matrix which is delay free. Next question. Prove that for every convolutional code has a polynomial delay free generator matrix. So for any convolutional code, we have an equivalent polynomial delay free generator matrix. So let us say we have a generator matrix which is given by GD, and this be any realizable and delay free generator for this convolutional code C, and let QD be the least common multiple of all the denominators of the non-zero entries of GD. So GD basically has a rational form and QD is the LCM of the denominator terms of the non-zero entries of GD. Now, if we have such a, and so we will have a QD which is basically delay free. So if we multiply our original generator matrix by this QD, we will end up with a new generator matrix G dash of D, which will be polynomial and delay free. Okay. Next. So let us first define a dual of a convolutional code. So we define a dual to a convolutional code C as a set of all n tuples of sequence V dual such that the inner product between this, which is defined as V and this V dual transpose, this is essentially 0. So if you have a dual to the original convolutional code, then if you take set of code n tuples sequence from the original code and the dual code, their inner product will be 0. So let us define a rate k by n convolutional code which is generated by a generator matrix G, and you know that we can write the generator matrix or convolutional code in a semi-infinite fashion. And let us say the dual code is this, which has rate n minus k by n, and it is generated by this semi-infinite generator matrix. Then show that G transpose basically will be 0, whereas G is the generator matrix of the original code and this is the generator matrix of the dual code. So, how does this follows? So, since V transpose is 0, so what is V? V is U times G, and V dual is U dual G dual. Now, we know that they will be dual of each other if V dual basically is orthogonal. So, if this inner product is 0, now if the inner product is 0, so then U G and this transpose should be 0. So, this we can write as U G G transpose U transpose. Now, this term will be 0 only if this term is 0 for all U, okay, and hence we get this condition that this should be 0. Okay. So, a convolutional dual to a convolutional code C, which is encoded by a rate k by n generator matrix G D, is set of all code words encoded by rate n minus k with generator matrix this, such that G D and the generator matrix of the dual transpose should be 0. So, the dual of the code is defined by this. Next. So, here we will show that the convolutional dual to the code encoded by the generator matrix G D is nothing but reversal of the convolutional code dual to the code generated by G of D. So, let us consider a rate k by n convolutional code which is encoded by a polynomial generator. We have already showed that we can find an equivalent polynomial delay free representation of any convolutional code, right. So, let us see, this is our G D for our original code C. Now, we define this as the reciprocal of the generator matrix. Now, how do we come up with a reciprocal? So, we do G D minus 1 and we multiply it by the maximum degree, which is in this case m. So, this is how we get the reciprocal. This is how we get the reciprocal. Okay. Now, what I have shown you here is the reciprocal of the generator matrix for the dual. This is the generator matrix of the dual code, and this is the reciprocal of the generator matrix of the dual code. Now, note, we have to show that the convolutional dual to the code encoded by G D is nothing but reversal of the convolutional code dual coded by G D. So, if that is the case, then G D dot product of G D with this should be 0. So, let us try to find G D and transpose of this reversal of the dual matrix. See, again pay attention to the question. Basically, what we are saying is that the dual of the code encoded by the generator matrix is given by the reversal of the convolutional code dual. So, reversal of the convolutional code dual is this, right. So, if the dual of the original code is given by reversal of the convolutional code, then what is the property this generator matrix should satisfy? This and this transpose should be 0. So, we have to show that GD and this generator matrix transpose is 0. So, we do this. So, this can be written as this term. Okay. Now, further we can write this as double summation, and what is this? This is the dual of generator matrix of the dual of this. So, this GD G transpose should be 0, right. So, this whole summation will be also 0. So, what we have shown is then the dual of this code which has generator matrix G is nothing but reversal of the convolutional code dual, because this generator matrix is nothing but it is a reversal of the generator matrix of the dual code of C. Okay. Next, we are going to show a bound on free distance of convolutional code. So, show that if you have a rate k by n convolutional code whose encoding matrix has memory n and overall constraint length mu, then free distance is upper bounded by this. So, if you have a rate k by n code, we can realize it using controller canonical form using 2 mu encoder state, because this overall constraint length is mu. Now, if we consider 2 raised power k into m plus I information sequences, then there exist 2k m plus I divided by 2 mu information sequence starting at 0 state leading to all 0 state. So, if we count number of such code words, then number of such code words m is given by 2 raised to power k into m plus I minus mu. And what is the length of this code word? Length of this code word would be m plus I into n, because this is a rate k by n code, right. Next, we are going to use Plotkin's bound. Now, Plotkin bound says it upper bounds the minimum distance as floor of, this is code word length, number of code words 2 into number of code words minus 1. So, in this example, what is our n? Our n is this. Okay, this is our n. And what is our m? Our m is this. So, if we plug in this value of m and n in our Plotkin bounds, what we will get is our desired bound, which is this result. Okay. So, the next problem that we will solve is to show that free distance of a rate k by n convolutional code is upper bounded by this. Now, this result can be obtained from the bound that we have derived earlier, this bound. Okay. And also we will show that this relation holds. So, since overall constraint length is less than k times m, then if you go back to this expression, v minus km is actually less than 0. So, we can then upper bound this by just 2 raised to power minus ki. So, if we do that, we get this expression. Okay. Now, how do we get this expression? So, we know that this term is less than 1, and so this we can just upper bound by m plus I by n by 2, and if I take m and n out, this will be 1 plus I times m by 2. So, d free by m of n will then be, so if I do further, d free by m of n would be upper bounded by 1 plus I by m by 2, and if we let m go to infinity, this will go to 0. So, that will be upper bounded by half. So, that is the proof. So, you let m go to infinity, and since this is less than 1, what you will get is this. Thank you.